Hi guys, thanks for tuning in. This is my second video from this chapter, and we're going to talk about how to do a 3D change of variables. For this first example, we're going to work out a problem that is very similar to a 2D change of variables that you guys did last chapter. If you remember, we integrated over a parallelogram-shaped region where our parallelogram was the intersection of 4 different lines. And in this case, we're going to integrate over a parallelepiped in 3-dimensional space. And we can create a parallelepiped by looking at the intersection of 6 different planes. And each of these pairs will be parallel to each other. Let me clear out some space here and let's take a look. All right, so here's our change of variables. Here's our clever change of variables. Let's look at this one pair at a time. So first of all, you might notice that I have z equals 3x. I can write that as z minus 3x is equal to 0. And then here I've got z equals 3x plus 2. I can write that as z minus 3x is equal to 2. And you could probably see where this is going. So I'm going to write u is equal to z minus 3x. And we can see right here that z minus 3x ranges from 0 to 2. So we're going to let u run from 0 to 2. And in a similar fashion, we can define v is equal to y minus x, and w is equal to y plus 2x, where v runs from 0 to 4, and w runs from 0 to 3. And you just kind of look at these equations pair by pair. So we can get v out of the second pair, and then we can get w out of the third pair. And we just use the same technique on each of those. All right, so our integral is going to be a lot more manageable because now we're going to be integrating in a UVW space where our region becomes not a parallelepiped, but a rectangular prism, kind of like integrating over a rectangle. Now we do have to consider a volume conversion factor. Just like in the previous chapter, you couldn't just willy-nilly move between coordinate spaces without making adjustments. And the same thing's going to happen here. If we want to map from an XYZ space to a UVW space, that's going to be a non-area, or in this case, a non-volume preserving map. And so we have to make an adjustment for that change. So we're going to need a volume conversion factor. But the trade-off here, the thing that makes this all worth it, is look at these limits of integration. They're awesome. These limits of integration now, they're constants. Looks like we're integrating over, in 2D would be integrating over a rectangle. In 3-dimensional space, it's integrating over a rectangular prism. So that's going to be great. Now the formula for the volume conversion factor is just a straight extension of what you guys remember from the area conversion factor. So the volume conversion factor is going to be a 3x3 determinant. And you can just see we've got 3 different gradient vectors moving across each row. So it just looks like the gradient of x with respect to UVW for the first row, and then the gradient of y with respect to UVW for the second row, and then the gradient of z with respect to UVW for the third row. So basically the same formula from the 2-dimensional case, just extended to our 3-dimensional context. All right, so just to generalize this, if we want to compute volume in 3-dimensional space and we want to use a change of coordinates, that's fine. You could switch over to UVW space. You just have to make an adjustment here by putting in the absolute value of a volume conversion factor, basically to account for the fact that we have non-volume preserving maps between XYZ space and UVW space. And in terms of our volume conversion factor, it is the same exact idea that you guys saw in the 2-dimensional case. It's just that now it's a 3x3 determinant instead of a 2x2 determinant, which makes sense now that we're in 3-dimensional space, a 3x3 determinant. And you'll never ever forget this formula because it looks just like the 2-dimensional case, but also it's just a matrix that you can create out of 3 gradient vectors: the gradient of x, the gradient of y, the gradient of z. Those will be our 3 rows of our 3x3 matrix. Now we do have to be careful again with positive and negative. So if we do end up in a situation where our volume conversion factor works out to a negative number, That's okay. Volume conversion factors can work out to be negative numbers, but when we put that volume conversion factor into our triple integral, when we start integrating, we need to put absolute value bars there. If you get a constant, just make that constant positive, and that is a good way of evaluating your absolute value. If you have something more complicated, you might have to put, in Mathematica, you might have to put ABS around it in order to account for the fact that the volume conversion factor needs to remain positive over the entire UVW region as we're integrating. Okay, so now we could finish up our volume of a parallelepiped problem. So remember, we defined UVW. You do need to solve a system of equations here to get x, y, and z. We need x in terms of UVW, y in terms of UVW, z in terms of UVW. You should know how to do this in Mathematica. You should also know how to do it as a hand calculation. But guys, it's not really that big of a deal. This is just a system of equations, and you're just solving a system so that we can isolate x and y and z. So not a big deal there. Now, once we have x as a function of UVW, y as a function of UVW, and z as a function of UVW, we are going to go ahead and compute our volume conversion factor. That's just going to be some partial derivatives, right? We need the partial derivative of x with respect to u, which would give us 0, x with respect to v, which is going to give us negative 1/3, and x with respect to w, which is going to give us 1/3. And we'll do that for each of those. And we'll build up a 3×3 determinant from that. You can see it goes in a similar fashion here. Look at y. The partial derivative of y with respect to u is going to be 0. With respect to v is going to be 2/3. With respect to w is going to be 1/3. And then z is the only one of these equations that has a u and a v and a w. So you can see we're going to have 1, -1, 1 for our row in our final row of our 3×3 determinant here. All right, so let's compute that 3×3 determinant. In this case, we get really lucky because we have a couple of entries that are zeros. So if you do expansion by minors across this first column, we could look at 1 and then this minor, and we end up getting -1/3. If that didn't make sense, you could just use any other technique you know for computing a 3×3 determinant. You don't need to use any shortcuts there, but entries that are zeros in these problems are welcome additions to our matrix because it makes computing our determinant a lot faster. So if you're able to exploit that, go for it. If what I just said about expansion by minors using the first column doesn't make sense, you could just use whatever other formula that you like using for computing determinants. Anyway, we get -1/3. It is okay to get a negative there, but when we're integrating, we need to use the absolute value of that quantity. So we're going to use +1/3 in our integrals. So now we can get our full setup. We already know our limits of integration from the previous slides. And now we have our integrand as well. Our volume conversion factor has an absolute value of 1/3. And then we're going to get 8. By the way, we can verify that 8 makes sense. There's a cool formula using vectors. So it turns out that this parallelepiped can be created by thinking about the 3 different vectors that would kind of make that parallelepiped. You know, I'm not great at drawing these things, but just like a parallelogram is spanned by 2 vectors, a parallelepiped, which I did not draw very well, but would be spanned by 3 vectors. And so if you could figure out those 3 vectors and plug it into this little formula here, the volume of a parallelepiped is x cross y dot z, where x, y, and z are 3 vectors that start at a point that kind of define our parallelepiped. That will get you the same exact volume. You don't need to know that formula. Don't study it for the quiz. Don't study it for the midterm. It's just a nice way to verify that 8 is a correct answer. So what I did is I just took these equations and I figured out 3 vectors that define my parallelepiped. And then I just plugged those vectors in whatever order I chose. Doesn't matter the order. I think I chose 0, 0, 2 for this last one just because it's nice to dot product with 0, 0, 2. Just makes that final calculation a little bit nicer. And then you get 8. If you happen to do competitive math contests, or if you're on math team or something, this is a formula that's worth knowing. But if you're not interested in doing competitive math contests, not something you necessarily need to memorize. I just wanted to show you that there is another way of getting the answer to this problem without using calculus. So pretty soon we're going to get to problems where you do need calculus to do these problems. We've now seen 3 examples across 2 videos where we had just geometry formulas and pre-calculus formulas that can get us our volume. Pretty soon we'll be doing things that are not going to be something you could tackle without calculus, though. And finally, for example number 2 here, we're going to try to compute the volume of a region in 3-dimensional space that doesn't have a nice geometry formula attached to it. So in this case, we have a football-looking region. We have a parameterization for the outer skin of that region, and we're going to try to find the volume that's trapped inside of this closed surface. Best way to start this is to understand our parameterization. So what we're going to do is we're going to break down this f of st into its various parts and try to understand how this parameterization leads to this football shape. Because if we understand the geometry of the region, we can probably set up a triple integral that works over that region. All right, so the first part that stands out to me is this 0, 0, 4s, where s varies from -2 to 2. That's kind of the central spine of our football. So you can kind of imagine the z-axis kind of piercing this football and kind of centering all of our circular cross sections that make up this football shape. Now you can see that if we have 0, 0, 4s, where s varies from -2 to 2, if you plug in -2, you get -8, and if you plug in +2, you get +8. So you can kind of see that this football shape goes on this, goes from z equals -8 up to z equals +8. All right, the next thing that we notice is our football is made up of a collection of circular cross sections that are parallel to the xy plane. I'm drawing a couple of them right here. They're not perfect, but I'm doing my best. So circular cross sections that are parallel to the xy plane. Let's see why that's happening. And we also see that the radii of those circular cross sections is changing as s changes, as z changes. Let's see what's going on there. All right, so if we look at this ordered triple, cosine, sine, 0, circular cross sections that are parallel to the xy plane. So that's why we have circular cross sections parallel to the xy plane. Now let's try to figure out what's going on with their radii. Well, that's going to happen because of this 4 minus s squared. This is describing the radius of these circular cross sections. And we just kind of want to think about what happens when s is equal to -2. What happens when s is equal to 0, what happens when s is equal to +2, and then we can kind of fill in the gaps in between. So when s is equal to -2, our radius is, the radius of our particular circular cross section at that point is going to be, what, 4 minus 4, which is equal to 0. Then when s is equal to 0, we have 4 minus 0 squared, which is just 4. And then when s is equal to 2, okay, that's 4 minus 4, which is equal to, again, 0. So what we have going on is a radius that starts out at, kind of the tip of the football. That's a radius of 0. Then it's growing, and you get a slightly larger radius, until we cap out at a radius of r equals 4. And then starts shrinking again, smaller and smaller radii, until we get to the top tip of that football where the radius there of that circular cross section is 0. All right, so that's how to understand plotting that region. Now, what we just described was the outer skin of that football. What we need to do is parameterize the entire 3-dimensional region, including the air inside of that football. So that's what we're going to think about next. How can we modify this parameterization to kind of fill in each of these circular cross sections? I need to fill in the space in each of these circular cross sections so that I can describe the full volume of my region. Otherwise, you can't really triple integrate, right? You'll notice that this parameterization has 2 parameters, which means it's a surface. It's the outer skin of this football. And what I need is something with 3 parameters that describes my solid region. And so to fill in that football, it's not such a big deal. I'm taking the exact same parameterization from above, and I'm just plugging in an r there, or I'm just adding a factor of r, and I'm going to let r vary from 0 to 1. And what to imagine here is that I'm taking my circular cross sections and I'm turning them into disks, because if I let r vary from 0 to 1, each of these circular cross sections will get filled in. And then what that will achieve is now we have a solid region in 3-dimensional space. So this is a parameterization for a solid region. And you could tell that that's the case because it has 3 parameters. Okay, so now we have our change of variables. We talked about this in the previous chapter, but what we previously discovered is that if we could parameterize a region, we could probably integrate over it. And that's what's happening here. If I can parameterize my solid region, I can triple integrate over that solid region and compute its volume. So my parameterization is my change of variables. You could see that x of rst is equal to r 4 minus s squared cosine t. If you're wondering where that comes from, look, I have an x-coordinate of 0, and then an x-coordinate of r times 4 minus s squared times, I'm going to distribute here to this cosine. Oh, that's what I have right here. Or let's try the y-coordinate. I'm going to switch colors here, and let's figure out how to get 4 times 4 minus s squared times sine. Okay, well, this y-coordinate is 0. Then I'm going to distribute that same r 4 minus s squared quantity to sine of t. Oh, yep, that matches. And then we're just kind of threading out this ordered triple, right? Let's try it for z. Z is really simple. It's just 4s. Oh, because I have this 4s here, and then when I distribute this scalar to 0, that's just 0. So I only really need the 4s, and there it is. Right, so as I previously discussed, if you can parameterize a region, you could probably integrate over it, and that'll be the case for this problem. So there's the setup for our triple integral. The only thing that I haven't figured out yet is my volume conversion factor. I'll do that on the next slide where I have a little bit more space. But the important observation before we move on is look at how wonderful these limits of integration are. These bounds for my parameterization are my limits of integration. And so that's a nice correspondence there. And the other thing that helps us realize is in XYZ space, this thing looks like a football, but in RST space, that football is now a rectangular prism. So this is the weirdest looking rectangular prism you've ever seen. Looks like a football, but in RST space, rectangular prism. All right, so the last piece that we need to work out here is the volume conversion factor. Here's where I wrote at the top of the slide that this is a Mathematica assisted change of variables. So can this be done by hand? Sure. I don't recommend it. I think this is best done by a computer because it's just very number crunchy, and you're not going to learn a ton by computing this Jacobian determinant. So you run this 3x3 determinant through Mathematica using the change of variables that we had on the previous slide. You just have to throw that r in front of the circular cross sections. Mathematica will crunch the numbers for you, and there's our Jacobian determinant. Now, we need to be careful when we're integrating here. We need to make sure that we're using the absolute value of this Jacobian determinant, of this volume conversion factor, because we want to make sure that at no point over our region do we allow this volume conversion factor to go negative, because if we allow it to go negative, we're going to get an incorrect answer. So we're going to take our setup here. We're going to run it through Mathematica, and then we should be all set. The volume of this region in 3-dimensional space is 2048 pi over 15. And then just as a check on this work, if you wanted to do this a slightly different way, that you actually could employ techniques from your Calc PC course by trying to understand this region as a solid of revolution. So when I drew the z-axis before, if you kind of pretend that that's a new quote-unquote x-axis, even though it's not the x-axis, that's the z-axis, but reframe that as the x-axis, and then try to find a curve right here that we can rotate about that x-axis. We can use, you know, a surface of revolution and find our volume of our solid that way. So you guys could see right here, this is stuff that you did back in your Calc BC course. So I'm just doing pi times the integral of r squared, where we have the radius of our, you know, the radius right here, this distance, and you get the same answer of 2048 pi over 15. All right, and that wraps it up for this video. So thanks again for tuning in. And in my next video, we're going to talk about how to use a triple integral to compute the mass of a three-dimensional region given a function that describes the density at each point.